Thank you, Hugo, and thank you for the invitation to speak here and talk about my work with Andreas. And the title of the talk is Gravity Without Averaging, and the archive number you can find here. Right. So I guess in the last sort of couple of years, there's been a sort of a renewal of some ideas of how we would think about gravity. I mean, in the beginning of the 90s, we saw a relation between gravity and matrix models, and sort of recently with JT gravity, a simple two-dimensional gravity theory again, that sort of revived the notion of matrix models. And these type of matrix models and the relation with gravity is a bit in contrast with what we know about the usual way we think about gravity in higher dimensions, in ADS-CFT. And basically my talk would be a discussion or a concrete model where we could try to marry those two or try to see how we can go from one to the other. So I made a little diagram. So gravity, or maybe more generally string theory. There's sort of two different ways of thinking about it, or at least how I'd like to think about it. So we have what I would call simple theories of gravity. And what I mean with that is basically gravity theories, which just contain the fields of supergravity. So and I know this is not very precise, but I just want to illustrate that too. And for these simple theories of gravity, it seems that the boundary dual of that, the way we think about these simple theories of gravity in a holographic way, would be in an ensemble. And we can compute these we can compute simple observables, and we find that there's correlation between, say, we have wormhole type geometries. When you have two asymptotic boundaries, we would have a wormhole type geometry for these type of simple gravities, indicating some correlation between quantum systems on either asymptotic boundary. So here, whereas on the other hand, the more complete theories of gravity that we know about, like string theory in 10 dimensions or N theory in 11, I'm just going to call that difficult theories of gravity. And, well, they will just contain the full string theory spectrum, all the fields that we would have present in what you would get from string theory. So all the fields beyond spin 2 are also present. There's no truncation, there's fluxes, etc. So an example of this is that famous example, I guess, superstring. And in this case, so for this more elaborate theory of gravity, we can derive things like the holographic correspondence and the boundary theory is a single theory. Okay. So, and of course you can go in between these two, or you can go from this one to this one by forgetting about some UV physics or a certain truncation. Of course, in this, so the objective would be to understand these more difficult theories of gravity, have a fuller understanding of the ADS CFT correspondence, or what it means, what we think of as a UV complete gravity theory. But of course, that's hard. The calculations that we would like to do in this theory, some calculations are very complicated, and we usually resort to a sort of simpler description, by which I mean we just take the supergravity approximation. And in that case, you'll land on what I sort of roughly think of as a simple theory of gravity. And in that case, we have evidence, or you can calculate certain observables like this wormhole type of geometry, where the boundary dual is not really a single theory, but an ensemble. So what this means is that when you forget about some of the UV physics, you sort of land on the boundary description to be an ensemble instead of a single theory. Nevertheless, we have examples of simple theories of gravity that where we can calculate things in a very efficient way. For instance, just the Sugra is a simple theory of gravity. We also have dilaton gravities that I would say are in this category. And one example that I would like to talk about today is this JT gravity. So that would also be a simple theory of gravity. And so JT gravity has an action. I'm just going to write down this action just to so this contains the metric, and here the Ricci scalar, and a scalar field phi, which we call the dilaton. And then there's also a boundary term that we add to make the variational principle well defined if the space has a boundary. Now, this theory of gravity is dual to a matrix ensemble, a matrix model. So this JT, this is dual to double scaled, doesn't really matter whether you know what that is. And this matrix model, a matrix model is just a matrix integral, basically, where you weight the matrix with a certain probability distribution, P of H. And then you can calculate observables that depend on your Hermitian matrix H. Yes, I should say that this matrix model is Hermitian, so this is an integral of the Hermitian matrices. There's some probability distribution that I draw my matrix from, and then there could be an observable. Say you want to compute trace H square of things that we would usually calculate are partition functions, so trace e to the minus beta h is another example of such an observable. And in this sense, you can see that this is an average. So we average over all Hermitian matrices here in order to calculate a certain observable. So we usually denote that with angular brackets. Now for JT gravity, this probability distribution takes a very special form. So for JT gravity, this P of H is so this takes the form of sort of a zero-dimensional action where this V, okay, I'm not going to write that right now. Point is that it's a single trace object, so it's the trace of some function of the Hermitian matrix H, and L here is the size of that matrix. And double scaling means that L is sent to infinity together with tuning certain parameters in this potential to specific values. So that's what double scaling means. Right, now the magic is that in JT, so this duality between JT gravity and this matrix model, what the new thing is compared to what we knew from the beginning of the 90s is that we can interpret this H as the Hamiltonian of the boundary theory. So there's really a way in which this is the partition function of the boundary theory. And when we compute averages of that, we compute averages of the partition function or correlation functions of the partition function. And there's a nice way to see that, but I won't go into that right now. But people that know a little bit about the minimal string theories, there's a certain limit of these minimal strings, of 2, p minimal strings, where p is sent to infinity. And the fact that this p gets sent to infinity requires you also to zoom in at low energies. And that effectively means that you look at very large boundaries, very large asymptotic boundaries. And that's precisely the setting in which JT gravity arises. I mean, there's some more words that I could put there, but that's all I wanted to say. Right, so the important point is that this H is the Hamiltonian of the boundary theory. So this duality tells us that we have an ensemble, we have an average over all Hamiltonians, all Hermitian matrices. And once I do that average, I compute the same objects as I would compute in JT gravity. For instance, this object here, if I would calculate its expectation value, in JT gravity, what that means, so trace e to the minus beta h, so this average with this particular probability distribution, this would calculate for me the disk partition function, where the length of the boundary is beta, but also all the other higher genus corrections. So you would have these type of things, etc. So you would calculate all these type of things directly from the matrix model. And of course, we know the matrix model also has a topological expansion, and that one matches precisely with the topological expansion of JT gravity. Okay, so that was just to say where this ensemble idea comes from. And the point now about why I was drawing this wormhole before was that if I now calculate something like this, then in gravity what that would mean is you calculate, so say I compute the connected guy, you would calculate a wormhole with here beta 1 and here beta 2, and then there's other higher genus corrections. And so this wormhole indicates there's a correlation between the two theories on the boundary. And so in that sense, there's a correlation and there's a non-trivial ensemble. These things, of course, you also find in these simple theories of gravity. If you set up a gravitational calculation where you have two asymptotic boundaries and you ask what are all the possible geometries that are consistent with those boundary conditions, and that's the Euclidean path integral that you're supposed to calculate, then you would also find these type of contributions. And so in such simple theories of gravity, you would also find these objects, and so you might conclude how there's also some sort of ensemble going on in the boundary theory. Now, of course, in these more difficult theories of gravity, you would also have that. You would also find this thing. But you'll find many, many more things. There's strings, there's branes. And so for these more difficult theories of gravity, there has to be a mechanism that sort of cancels the correlation so that this connected correlator sort of would vanish, as you would expect if you have just one single boundary theory.
I don't know, not really technical, philosophical question. Like if you have like this left-handed supergravity in high dimension, then you see you compute the corrections even in bulk, and then you see the necessity of infinite number of terms.
Yeah.
And then of course to take care of that in a super-Planckian regime, you relate to string theory, and then you see the D-brane by studying that theory, and then you see
of course
10 dimension and so on, right? You relate to this. Is there any analogous in JT?
No, well, I mean, of course, the matrix model, double scaled, makes sense on its own. You can ask about, is there different non-perturbative completion of that matrix integral? And I guess there are different ways of completing that non-perturbatively. But that's more about the genus expansion, like a topological expansion. So it's not so much about the divergences that you're talking about. Because here, in this case, the G Newton is like dimensionless. So.
I just wanted to know analogy is not complete or.
Yeah, I don't think it's yeah, that's right.
That's still fine.
Yeah, that's right. More questions, comments? Okay. Right, so let me tell you what I wanted to do today. So what I want to do today is to see if we can change JT gravity a little bit so that we sort of land more into this quote-unquote difficult regime where we have a single boundary theory. I do not mean to include in JT gravity strings or those type of ingredients. What I want to do is change the matrix integral and see whether I can deform the matrix integral with a parameter that allows me to interpolate between having this ensemble and having an ensemble which is basically a delta function. Okay, so first thing is that's the first thing. And the second, I think I also already said. Right, so how do we do that? How? And second, so then we'll see what type of lessons we can learn from that. What we can learn from that. All right. So, are there any questions at this point? No. Okay, so one way to change the matrix model potential to go from an ensemble to a single theory is in the following way. This is just very simple. So we have our observable O, and what I want to propose is to study the following model. So I'm just going to insert a Gaussian in this matrix model that is centered at some fixed matrix H0. And so when sigma is very large, this Gaussian basically does nothing. But when sigma becomes small, this is very peaked, and I basically pick out a single Hamiltonian in this integral. And the quest for today, or at least part of, would be to understand what this means gravitationally. In JT gravity, what is the dual of this? Furthermore, let me comment that, so everything is going to depend on this matrix H0 that I picked here. If I average again over H0, so do the integral over H0, then this entire Gaussian disappears, and we're ending up with the usual JT ensemble. Okay, so there's one thing that makes this matrix model a bit more complicated than the usual one, is because of this mixed term here. So this guy contains a term that goes like trace H, H0. And so usually what you would do in this type of matrix integrals is you would diagonalize H. And so you would write H as U, some diagonal matrix lambda, U dagger, or U is a unitary, and decompose the measure over Hermitian matrices into these type of, an integral over unitaries and an integral over the eigenvalues, this diagonal matrix. And that works for this one. This only depends on the eigenvalues, and the unitary integral decouples. And for the terms here, inside here as well, except for this term. So this term becomes and so the unitary integral here is non-trivial. So without this term here, of course, I'm assuming that these things are all, I guess, trace class is what you would say, these observables. so that these also don't depend on the particular unitary. But this term, at least the mixed term, will depend on the unitary. And so when we do this decomposition, the non-trivial integral, the sort of the difference between this matrix integral and the usual one is just this unitary integral. And so if we want to find a gravitational interpretation, we need to find a gravitational interpretation of this guy. Now, luckily, you can calculate this exactly using what's called the Harish-Chandra-Itzikson-Zubair formula. Or in more modern language, maybe, this integral is one loop exact, and which follows from this theorem by Dijsselmaat and Heckman. And so you can calculate the saddle points of this action and calculate the quadratic fluctuations around it. And what you find approximately is something like this. So this is a determinant of the matrix, so I and J here. Hope that is clear. The x's are the eigenvalues of H naught, so that's the matrix that we put in, sort of the external matrix. And these are some van der Monde factors, so they're pretty explicit. So delta lambda, this is product I smaller than J. Like that. So this is all very nice. We can calculate this integral exactly, try to put this inside here, and then see if we can understand that gravitationally. Now that turns out to be rather complicated to use this particular expression to get something, or to double scale and try to understand what happens geometrically. So instead, I'm going to do something slightly different. So instead, I'm just going to use these angular brackets for the unitary integral. I'm just going to use this famous formula that I guess we all know, but I don't know by heart. Let's see. And then here we take the connected component. And so this is the usual statement that the exponent, that the average of the exponent is the exponent of the connected correlation functions. And so this is an exact statement, and you can calculate these type of correlation functions sort of easily. And what I want to do is approximate these particular correlation functions. And the limit, so there's yet another approximation here. So sigma here, in principle, this is an exact formula. However, when sigma becomes very small, this sum might not converge, and I still don't know what to do. So what I will be interested in is large sigma. So sigma squared is much bigger than 1. And in that case, this sum will converge, and I can actually calculate these correlation functions in a simple way. So to first order, and also remember that so L is also much bigger than 1, and L is the, let's see, L is the largest parameter in the discussion. So these unitary integrals here, so this angular brackets means unitary integral. You can do those easily with what's known as Weingarten calculus. It's not very essential to know right now, but for instance, the first contribution in L has this form, and then there is order 1 over L corrections to that. Okay. So I know this is a bit abstract, but I'll get to some sort of point. So this type of correction, so if we just keep the leading term here, this reduces to exponent of logarithms, right? So here we get, let's see, there's a sum over minus 1 to L, and then there is trace log. So the first correction to this unitary integral, the leading piece is this trace log, and then now I can write this as, let's see, there was a minus sign here. So then this is a product of determinants. And for convenience, I'm going to take out some factor. So, okay, so what did we learn with this exercise? So this unitary integral means that we're basically looking at a matrix integral with some determinants inserted. And, well, determinants we know very easily how to interpret geometrically and interpret in JT, because they're basically branes. So they correspond to branes on which the space-time can end. And the branes in this case, they depend on the sigma. So the branes have a parameter, and the parameter depends on what the eigenvalues of H naught, the matrix that I wanted to fix to, what they depend on, and on this parameter sigma. And of course here sigma is very large, and so yeah, so that's the approximation that we made. So fixing the Hamiltonian a little bit means inserting branes in the gravitational description. Okay.
Until now, you were working entirely on the boundary side.
Yes, right.
So it's purely manipulating
of this boundary. Yeah, right. Exactly.
Can you discuss the connection with the branes in a little more detail?
Right. So these determinants. So basically, this trace log. So yeah, I mean this. It's a bit long to explain, I guess, what precisely the connection is, but let me just maybe say in a few words. So so we have here the exponent of something trace log something minus h. So trace log. Say I want to calculate something like this. What you can do, for instance, is doing an integral like this. Right, remember z of beta was trace e to the minus beta h. And by doing this integral, okay, it has a divergence here, so let me cut that off. I'm being a bit schematic here, but okay. Now you see that this partition function here appears in the exponent. And how we think about branes is a place where the space-time or the geometry can end on. And so why we think about this as being branes is because, again, here we have an exponential number of boundaries. So say you expand this in the number of boundaries. Let's insert this expression inside here. Expand the exponential. You get a term that corresponds to 1 boundary, 2 boundaries, 3 boundaries, and so on. That's typical for a brane. There's other, so that's a sort of maybe a bit too intuitive picture. There's also another way, but I don't know the details there, is to think about it from the minimal string perspective. That you can think of these trace logs as in the minimal string theory, you can think of those as certain boundary states. These are the.
What type of brane should I be thinking of here, and how is it related to the parameters of appearance expression like sigma?
So the brane here depends on a parameter, which, okay, from the minimal string perspective, which is sort of maybe the most correct perspective to take, these branes originate from certain boundary states in the Liouville theory that you have for this minimal string. So this boundary state of the Liouville theory, that translates into on the dual matrix side, into calculating this particular object.
So they're like 0 branes in different states?
So these would be, these are called FCCT branes in this Liouville nomenclature. So these would be, I think they would be 2-dimensional. Yeah, I don't know how to think about them as D0 or whatever, D2 or.
What kind of objects are being introduced and how it depends on sigma, for example. I mean, it's going to be. What you're doing is basically varying sigma away from infinity, right?
Yeah.
So is there some way of describing physically what is happening here? The sigma is just very, very large.
It's probably more intuitable, not the last line, but next to the last line, and you expand the log, right? That's xi h or sigma squared.
Yes, yes, yeah.
So you have xi instead of beta. So if you have a multiple e to the xi over sigma square h is equal to e to the minus beta x. So you have extra boundary corresponding to xi, and the coupling constant being 1 over sigma square. So if sigma goes infinity, those things decouple.
Yes, that's
so
true.
So you expand this and then compare with e to the minus beta h, because this takes the form of e to the minus xi h over sigma square.
Yes, that's.
So that's a multiple.
So
These are multiple boundaries.
So there's one per boundary. There's one per eigenvalue for each knot, and
Yeah,
over
that's.
sigma squared is like the coupling.
Yeah, it's a coupling constant, and that will be coupled, because you can see it goes to infinity.
Yeah, those things, that's indeed true. From a more, I guess what Yasunori is saying, from a more ribbon graph perspective, if you expand the trace log, you get more and more of these vertices, and okay, if you run that through that logic, you also find that indeed there's branes and they have certain coupling, certain holes in the space-time, and there's coupling constants xi. Or, yeah, there's for each I there is a brane coupling constant.
But so then there's some sense in which the number of species that are being introduced is always the same. It's just that they're not coupled.
Yeah.
At sigma equals infinity.
That's right. They decouple.
And in fact, the number of species is being introduced exponentially large.
Yeah.
Sorry, it's as large as the matrices.
Yeah. That sort of makes sense, right? We want to fix the entire. If we fix the entire Hamiltonian, we would need as many brane or as many parameters as those. Yeah. That's right.
So in the semi-classical limit, I'll have an infinite amount of branes as I go through infinity, is that correct?
That's right. That's right. Yeah.
I mean, if I think of this as modeling some sort of black hole of area, and even the number of branes that we're introducing is of order e to the a over 4.
Yes.
It's what is the engineered black hole?
Yeah. So that is, of course, a little.
Naive, but I mean, if I introduce this many species in a bulk theory, normally I would lose control of the theory.
That's true, and you will. If sigma is very large, then you can treat this all perturbatively, and that sort of works. But when sigma becomes too small, actually you get contributions from very high traces, the h to a very large power. And well, that means basically that the space-time, it ends on the brane, but the boundary on the brane becomes very big.
Oh, I see. Yeah.
Beta is an xi over sigma.
I mean, this boundary here.
Jorrit, sorry if you said that already, but is L sort of like e to the phi naught in the semi-classical limit? Or is that how I should think about it?
Well, L really goes to infinity.
Mm-hmm.
And in the double scaling limit, so the spectrum has a certain edge, and you would send the edge to infinity, and you would send L to infinity as well. And the ratio, like L over E edge to some power, that's usually called e to the s naught.
Oh.
Yeah. But since L directly appears here, this goes to the L here goes to infinity. Yeah. Okay, so right. So maybe a bit more. Let me maybe go on. Right. So now that we understand a little bit what happens if we slightly fix the Hamiltonian, we have these branes in the space-time, an infinite number. What we would like to understand is the double scaling limit. And the double scaling limit is where we can really understand what the space-time interpretation is. Okay. So there's sort of two ways to do the double scaling. One is a more non-perturbative way of looking at things, which is using orthogonal polynomials. I won't be discussing this, but just and this is more non-perturbative. And the second one is sort of a more down-to-earth way of thinking about it, and that's related to Hugo's question, is you send L to infinity, and the spectrum has a certain edge. I'll come to that in a minute, which we also send to infinity, keeping the ratio a certain, keeping this fixed. Okay. So the idea, so what is this edge? So when we diagonalize the Hamiltonian in this matrix model, we can write down in the large L limit, we can write down a density for the eigenvalues. It's rho of E. And for instance, it can be in a Gaussian matrix model, I'm sure you have seen this, this would be the semicircle. But if you have more complicated potentials, such as the one in JT, this looks a bit more complicated. So I'm just going to draw it here schematically. Should roughly be symmetric, thought of as symmetric. And so here there will be some edge, called that M0 here. So imagine, for instance, that this would be the density of the eigenvalues when I don't have this insertion. So we're at sigma's infinity and there's no branes and everything is decoupled. And I have this, the spectrum looks like this. Now, you could imagine that when I insert these branes, this spectrum is going to change a little bit. And there's going to be some new edge, like so. And this E naught, how it sort of differs from M naught, you can calculate that exactly, how that shifts if you insert these branes. And the double scaling limit is then defined as follows. So I'm using the old edge. So this is how you define the double scaling, and here M naught is this M edge that I defined there. So this is going to be sent to infinity with a certain ratio like that held fixed. And now looking at these determinants, you can also convince yourself that sigma and the xi, you also need to scale those in order to get something workable in the double scaling limit. And what you need to do is send sigma to m naught plus sigma, and the xi's we scale in exactly the same way as we scaled the energy for the density of states. So the energy and the eigenvalues xi, they sort of, you scale them in the same way, which makes sense, of course, because the E here can be thought of as the eigenvalue of the Hamiltonian, or like the distribution of eigenvalues, and so the xi better scale in the same way. And what you get then is so then you calculate what the new density of states is when you insert these branes. And okay, I don't think it's necessary to give that particular expression right now. But the nice thing is that you can translate that deformed density of states to a particular change in the dilaton potential of JT gravity. So maybe let me be a bit more precise. So let's call rho naught this one. So that's without the branes. And then this one will be rho. And rho naught, for instance, is in the case of JT gravity, this will be the Sinh hyperbolic at the density of states of the Schwarzschild theory. And rho will be a correction to this Sinh hyperbolic. Now, people have worked out how to go from a change in the density of eigenvalues to a change in the dilaton potential of JT gravity.
Before you do that, should I think of that? So this works as long as the sigma is still very large, right?
That's right.
And should I think of that as a sort of force, well, I don't know, as a description where you iterate all these new branes out and sort of
Yes.
absorb into the change in the...
Yes. Yeah. It's like an open-close type way of thinking about it. On the one hand, you can think about having all the branes and all the extra boundaries, or you can think about it as a change in the dilaton potential, and there's no branes.
But from the second point of view, it's kind of clear that we're still talking about classical, I mean, it's sort of semi-classical gravity theory.
Yeah.
In the bulk.
Yeah, so in some sense, this second perspective is nicer. Yeah.
It's very nice, but you could also say that you haven't really, I mean, if I wanted to be negative about it, I would say, wouldn't you worry that you haven't really moved away from the semi-classical description?
That's right. That's right.
And you would... It's kind of like saying you can only move away in a sort of phase transition kind of way, but at some point you just can't do this anymore.
Yeah, so let me write down the potential, and then we see that indeed such things happen. So let me just write down the JT action again. And then I wrote it like this. So we have R phi plus now U of phi. And then U of phi is given by the following expression. So it's just the JT. This is just the JT part. Let me not call this JT. And then we have a correction that goes like this. I'll just write this down in a little bit, what these things mean. where this guy is given by so this guy is given by 2 sigma plus xi to the. Okay, so the change in the dilaton potential is of order e to the minus s naught. So this is precisely correction what you expect from a brane. And it creates one extra boundary, so it increases the Euler character by 1. And then here there are a bunch of terms that depend on the dilaton potential. And so this works as long as sigma is very large. If sigma gets small, you can see that there's problems here.
So the index I appears in the first term for alpha 0?
Yeah, so maybe, yeah, let me.
And in the second term?
And the second term, yeah, sorry. Good catch, sorry. Yeah, like that, sorry. Right. So here you see that there can be certain divergences occurring when sigma becomes too small. So say xi is as a negative eigenvalue, and this quantity is not positive anymore. Then there's a value for phi where this blows up, or this guy can blow up. And so one of the points of our paper was that at very large sigma, everything is fine. We have a very nice description. The dilaton potential gets a little bit modified. But once you make sigma a bit smaller, you start seeing sort of funny features where the correction to the dilaton potential becomes very large. And there is a way of understanding that, but I think I won't have time to discuss that in detail.
But you discuss just what characterizes the value of sigma at which this transition happens. So should we compare sigma to the
So,
negative eigenvalue, or
minus xi over 2?
So that's right. But there's an interesting way of analyzing the transition. It's actually was already like pre-branes and stuff discussed by Kazakov, that if you have these type of branes, so these inverse determinants, you could have sort of transitions where the space-time where it ends on the brane, these boundaries become very, very large. If you look at this type of picture, basically what happens is that there's an eigenvalue that comes in from minus infinity and tries to enter into the cut, into the distribution of eigenvalues. But it can't really enter because once this eigenvalue, because we have this parameter sigma, I can tune when this eigenvalue sort of hits this m naught, the cut of the eigenvalue is going to change. So it's going to just move a little bit. So it sort of repels the eigenvalue and the edge, they repel. And yeah, that you can see as a transition when this E naught becomes non-trivial. So yeah, maybe once again, so there's an eigenvalue sitting here, say some xi, that now tries to enter into the eigenvalue distribution. But when it tries to do so, the eigenvalue distribution reacts to that by just moving a bit to the right. And sort of that is one way of interpreting that, and that's one way of interpreting these divergences that happen here. Right. So I think my time is up. So these divergences, of course, keep on happen. So there's a divergence for the largest negative eigenvalue, and maybe you can find a description where you go to the other side of that transition, but then there's many other of these eigenvalues as well. So the other type of branes that can then have a large boundary. The other thing that breaks down at a certain point is that, remember that in this unitary integral that I had.
I'm sorry to interrupt you. Just intuitive. So, is it correct to think of sigma as it's sort of the standard deviation around the value to which you're localizing the matrix? Right?
That's right. Mm-hmm. Yeah.
So it means that you're localizing to matrices which have, which is the one that you want, plus or minus some energy scale sigma for every eigenvalue. Is that right?
Yeah, that's right.
And so the space transition happens when that tolerance becomes smaller than the characteristic energy scale of the original H naught. Is that right?
That's right. Yeah. Yeah.
So in fact, you have. So if we want to be on the good side of the phase transition, we have sort of completely failed to localize it. I mean.
Yeah. No, you're right. Yes.
Much bigger than.
That's right. That's right. And yeah, so this happens like very quickly when you start decreasing sigma away from infinity, I guess.
So there's some sense in which we're also not really, just as there's a sense in which we're still doing semi-classical gravity, we're still doing what you call the simple gravity theory.
That's right.
There's also a sense in which we aren't really at all localizing to specific boundary theory.
Yes.
So the match is
yes.
very nice. I see.
No, that's definitely true, and maybe one more piece of intuition. I mean, it's more from the finite L matrix integral. So what is this insertion of this Gaussian doing? So we start here at sigma's infinity. We, for instance, have the semicircle. But all the way here, at sigma 0, we just have a bunch of delta functions. And so how do you go in between the two? Right, so one intermediate, so this you can calculate exactly in a Gaussian matrix model. So you would start seeing all these sort of wiggles that become very big. And at some point, they would hit the real axis and you get a gap here. So the matrix integral actually goes from what's known as single cut to multi-cut. And at this point, it's not even clear what the gravitational interpretation is. Because usually, like what I was trying to explain here with this double scaling, is that you're zooming in to one of the edges. So if you want to zoom in here, that's fine at sigma's infinity. But once you're beyond this, like do you zoom in here, here, here? What's the precise prescription? So it's not even clear how to recover or how to come up with a gravity theory in this case. And that will be already intermediate. Yeah,
But is that transition where you have the first, I
Yeah.
That's not exactly the same as.
No. Yeah, that's not exactly the same as that's right. Yeah. That's another effect that reminded me of your question. Yeah. Right. So yeah, that's basically all I wanted to say. Just a couple of remarks maybe to finish. I was doing a lot of approximations. So I had this unitary integral. And I kept a certain term here, or a certain bunch of terms. In particular, I only kept terms that went like trace H, like single trace guys. When sigma becomes smaller, you could also worry about multi-trace objects contributing. And what is the gravitational interpretation of those? Well, people have looked at that for certain double trace deformations. And basically, if the coupling of a double trace, so say something like this, with some coupling G, when G becomes too big, you enter in a branched polymer phase where, okay, the geometric description even breaks down as well. So, and I don't know whether this is connected to this, what I was saying, but that's one thing that should be kept in mind. Yeah. Of course, this entire idea of putting in this Hamiltonian at some this Gaussian, you can also do that in SYK, try to calculate, insert this, insert something like this, where some j minus some j0, forgetting what the indices now, and well, you can try to see what is the SYK interpretation of that, how does these saddle points that people like to find for SYK in this G sigma formulation, how do they change under the influence of this external field? Yeah, so that's, I think, another interesting way of maybe connecting or trying to see whether there's also a gravitational interpretation if you view it from the SYK perspective. So, yeah, that was it. Thank you.
So, questions?
Do you know that when sigma was brought down from infinity and then it goes to space function,
Yeah.
you lose the simple description of space-time with modified Dirac term. You lose that. Do you know that there is no space-time description? Or at least this wave description just breaks down and have to go to something else you made? Or it's not clear, or you already know that there is no such description?
Well, on the other side of the transition, the only thing that I know that happens is that these the space-time, the boundaries on the brain, they're very large. That's something that happens in that limit.
So
that would say to me that there's no. Oh,
yeah, naively it's not.
Yeah, but on the other hand, it could be that the approximations that I made, if you include more corrections, they might alter that transition so that it becomes smooth in the end. So maybe it's an artifact of the approximations that I made that you're seeing this transition.
Oh, in other words, this question, if the boundary, like the length of the boundary of the brain,
Not asymptotic, yeah.
if this becomes large, then naively it looks like sigma of order xi is a bad point.
Yeah.
And then that means that this length is like x over sigma squared, so it's like 1 over x.
Mm-hmm.
And so you can trust up to that. that means that this becomes macroscopic, or in a sense of all the data which you want to take as E.
Yeah.
You can still trust and become like huge hole.
You're saying that, okay, it becomes like an asymptotic boundary,
Yeah,
even in that.
comparable to that or something.
That's right. But also yeah, that's true. I guess the boundaries that end on the brain are slightly different. So say here is the brain. And I think the boundaries that end on the brain, they're geodesic. So I think so, that the extrinsic curvature of the boundary on the brain is 0. And that means that, like, that means that the area of I think that means that the area is still still small. So even if this boundary becomes very large, you're not getting more area, so that the space-time would look like very thin. So it's a bit different from this asymptotic boundary, which has k bigger than 1. This asymptotic boundary. Yeah, it becomes like a bunch of, like a thin strip, basically, yeah.
Is the dilaton also small over there, or is it also growing? Because there's also an interpretation of dilaton saying the size, right?
Not.
Even if the dilaton is like going up.
If you have an annulus, right, you shrink the width of the annulus to 0, you still have no space time. It doesn't matter how big the annulus was to start with.
Yeah. Right.
A little bit confused with the final conclusion is because we cannot have like this sigma goes to 0 because the potential diverges. Should we expect something of similar mechanism in the higher dimensional ADS-FT or not?
No, I think when sigma becomes very small, I mean, I think the only thing that this is saying is that when you want to fix the entire Hamiltonian to something, then you need to put these infinite number of branes. Now that goes wrong at some point. I don't think that in n equal 4 super Yang-Mills there is something like that. How I think about the analogy there is that these would be sort of bulk couplings that now appear in the bulk theory. So the bulk theory in n equal 4 super Yang-Mills is very specific. We have very specific couplings, and this prescription shares that same thing. But I don't think that, I mean, n equal 4 super Yang-Mills, like the bulk is just known. There's no divergence of any potential or something like this. Now, it could be that, and the approximation, as I was saying before, the approximations that I made led to this divergence. And so maybe I need to do a bit more work to try to analyze that and see what happens. It's also slightly different because you have this type of phenomenon occurring where it goes from one cut to multiple cuts. Okay, that we also don't have in that in that description. I mean, in some sense, like the n equal 4 super-YAML is like that's just here. Like we're just exactly here. So, and I guess it depends on what type of questions you're asking. Are these questions that you could also answer with like the simple theory of gravity, or do you need some more complicated things, the complicated ingredients that you have in superstring theory? So those, yeah, that's also different.
Any more questions? No, let's thank him again.